Good evening, all. So, hope you would have had through your group email. So, and I have included all the topics, a brief about all the topics in the PPT with respect to the unit one. And in the last class, we had been discussing about the colors, and the human perception of a color, the physics of a color, and how do we represent color, right, with a linear or non-linear space. That's where we started our discussion. And again, to continue from that one, right? So what we were discussing is before the representation of a color, we already discussed that how to match a test light with the help of three different primaries by tuning their weights, right? So that's what we have discussed, and it's just a small set of assignment, the task or experiment which people usually do to analyze how a human being is perceiving color information, right? So in that same line, uh, if we have any set of primaries, we could able to estimate or obtain a color matching function, right? So that's what we discussed earlier. So what we will be doing is we will have some W1, W2, W3 weights corresponding to P1, P2, P3 primaries, and then we will be able to adjust or tune these weights so that we can able to generate a light which is very similar to our test light, right? So that's what the color matching experiment what we were discussing earlier, right? So we tune the weight of each of these primary to match the light from the source, right? And what people usually will be doing is, so we will record all this information in a table. For example, we'll start from some random initial weights, some W1, W2, W3, and slowly iteratively what we will do is we will tune these weight values so that we are matching our the test light, right? So in that case, all this different values of W1, W2, W3 and their corresponding wavelength what we are obtaining, right? So wavelength of the light, all that we are recording in a table, right? So these table are the color matching functions. See, for example, when we vary different weights, we will be generating different color of lights, right? For example, we have chosen RGB, right? Red, green, blue primaries. And the test light, given test light is an yellow test light. So now what I have to do is I have to tune this RGB weights in such a way that the output from the source is also yellow, right? Is also yellow. Now in this case, what we will be doing is we will start with some random weight values so that maybe like the generated light may be red in color. Sorry. Initially, some light red in color. Then if I slowly change the weight values of red primary and as well as blue primary, what will happen is from red, I will be getting an orange, right? Orange color. So then slowly if I tune the weight some way from orange, the color will change into yellow, right? So in between, for different values of this W1, W2, W3, I'll be getting different colored lights. So all this I'll be recording, in a table, right? So along with their wavelength, right? So because wavelength decides the color of the light, so these table are the color matching functions for us, right? So for a particular lambda, what are all the weight values, right? That will help us to get this color as an output when RGB is being used as a primary, that we can able to know, right? So the same mathematically if we want to represent, right? So u of lambda naught, right? That is a test light. U of lambda naught is here the wavelength of the light source, equal to f1 lambda naught p1 plus f2 lambda naught p2 plus f3 lambda naught p3, right? This is nothing but, right, the same weighted primaries function, w1 p1 instead of w1 here f1, right? F1, f2, f3 are the weights required for to match the source light, right, at that particular wavelength lambda naught, right? Now no, for example, to apply the same logic, right? To apply the same logic over our function, mathematical function, right? I will show this also so that it will be more clear for you. Right. So this is what we are discussing now. U of lambda naught equal to f1 lambda naught p1 plus f2 lambda naught p2 plus f3 lambda naught p3. So f1, f2, f3 are the weights which are required for us to generate that or match the test light, right? So now in this condition we are using a one more rule that earlier we have discussed, that the overall response of a receptor for an incoming bunch of light ray can be computed with the help of a integration over the sensitivity product of sensitivity and the energy, that already we know that. So the same one we are going to apply here to estimate the W1, W2 and W3 values. So we use the same logic, right? Integration over F1 lambda multiplied by S lambda, right? So this is for estimating the value of W1, right? Instead of W2, integration over F2 lambda product S lambda, right? S is nothing but the the source energy here, right? So this is what a way of uh, color matching actually, right? Color matching by with the help of. So now in this representation of color, right, we will be having some issues. We will discuss that, right? Here we are using some primary colors for mentioning or specifying a color. For example, when we go to now till also when we go to some Photoshop or any other photo image editor. And in any image editor, right, if you look at the color palette, you can able to see, and if you click on or if you select any color, particular color, their combination, that is RGB value, you will be seeing it up, right? Because that's a combination of these three primaries, R, G, and B, right? So, but what is the problem here is, at one of these color matching functions will be negative for some wavelength, right? So we have seen that. So for estimating the W1, we are using certain color matching functions, right? Here F1, F2, F3, right? So in that case, at some wavelength, for some wavelength, right, these color matching functions value will be negative. So that what will happen is, we need to include a subractive matching also into our logic. Subractive matching in the sense, what we are trying to form out is a additive matching, right? Additive matching is the sense adding three primary colors R, G, and B. We are trying to represent a color here, right? But instead, sometimes we may be because of wavelength issue, any one of right, any one of matching function will be negative for some wavelength, right? So at this case we require a subractive matching. To understand about this additive matching, subractive matching, I'll tell you this example. For example, if you see newspapers, color newspapers like Deccan Chronicle or Hindu or whatever it is, you can see in the bottom they will be giving like CMYK, right? Now for printing, we will not be using this RGB. For example, in case of computer monitor or a color television, right? Earlier we are using a RGB, as the primary, primaries. So they are the TV or the monitor or whatever it is, the displays. They are emissive devices. Emissive devices in the sense they will emit a light ray, and because of the combination of these different light ray, we can able to see different intensities or the different colors actually. But now The difference lies here is, in case of printing technology, we are going to print some color font or color text over a white background, right? So white color of the paper is white, right? So on the white paper, we are going to print something, right? Now in this case, for example, we will be for if we want to bring out a black color, right? If we want to bring out a black color, so what we need to do is we have to mix more colors here. Then only we can able to get a pink or light color if I want to get out, right? So very close to white or some white light shade, I have to spend more ink to generate this color in paper, right? So I have to use more red, more green and more blue so that I can able to get such a color, right? So instead of that, if I use subtractive, right, cyan, magenta and yellow, right? So which means that, right, I'll show you that also. Now you can see this one, right? So for printing technology, we use this subtractive, right, color, C, M, Y, and K. So K is nothing but for for getting a black color, right, on the color, some font printed on the paper. We have to use more ink. That's why separately we have a black ink, right? Forget about it. Now, for example, here you can able to see that the cyan is a color, right, which we will be getting when we mix blue and green, right? So we don't require red actually, right? So now what now also like the magenta is the color when we mix this red and blue, right? We will be getting magenta, and red and green we will be getting yellow, right? So but one more thing we need to understand is when we mix all the CMY, right, color, even in whatever the ratio, we will not be getting the perfect black. So we'll be getting a imperfect black or some dark gray, right? So in that's why we have a separate. Also for that reason, we have a separate black ink actually, right? So how this printing CMYK based printing on a white background will function is, uh, the model works by partially or entirely masking colors, right? Instead of printing, we are masking colors, right? The ink, that's why we can able to reduce the amount of ink which we are spending actually, right? So what we need to understand is white light minus red, we will be getting cyan. White light minus green, we will be getting magenta. And white light minus blue, we will be getting yellow, right? So whereas in additive color, right? So the combination of these primary colors, we will be, right, able to get a color, new color. But in case of CMYK, it is opposite, right? So white is the natural color, right? Or usually all the paper, whatever, wherever we are printing, it is white actually, but the black results in a form of no combination of colored inks, right? Full combination, right? To save the cost on ink, right? And to produce more, right? And produce deeper, no black color tones, right? So what we will be doing is, no, if we use R, G, and B for it, we have to spend more ink. So instead of that, so we will be using a subractive matching technique. With that, no, we can able to spend a less ink, right? So the advantage here is not only on the no saving, or the reduction in the amount of ink spent for printing, but also on the process involved in it. For example, if it is an RGB, frequently refilling that cartridge may be required. But if you use the CMY based printing principle, we'll be spending less ink, and the amount or the number of prints taken will be more. See, that's what the difference between additive and subractive printing, right? So in the same fashion, right, here in the process of generation of light ray. So if we use this three primaries, red, green, and blue, for generating a new color, some of that time, right, at a particular wavelength, the color matching functions will be negative. So to represent that color, right, we may be requiring a subractive matching, right? So that's the one issue in this linear color spaces. So how do we avoid this problem is to specify color matching functions, right, that are everywhere positive. So at the time we will not be requiring to represent a negative coordinate, right? So what we have to find out is a color matching function that is everywhere positive, right? So that is what we need to find out. So for this no process of representing a color with three primary colors, we have different color spaces, and one such is an XYZ color space, which is a popular standard. The color matching functions will be positive everywhere, so that the coordinates of any real light are always positive. Now, like this space is nothing but, so in somewhere else we are going to notate. For example, um, if you want to represent the any three-dimensional object, right? Any three-dimensional object, right? So I think the main drawback is you have not you don't have the engineering drawing subject, so that's why making you clear with some concept is more tough for people. Okay, fine. So now what is we are going to do is we are going to use some color spaces wherein we are going to represent a color. For example, a 3D object, right, can be represented in a three-dimensional space. No, a 3D object with its length, breadth, and width, right? So if we have all this height, the height and whatever this. So when we have this three-dimensional measurements, for example, right? If we draw this one, you will be more easy to understand. Right. Now we are discussing about representation of color. To make it now clear about the concept, I am drawing or I am representing a one cube, right? One cube in a three-dimensional space, right? Now, for example, what I will do is I will have represented as a dotted line now, right? Now what I have done is I have right I have a cube now which is available in the three-dimensional space. So that what I can do is I can represent each of its coordinate. Right now I have here uh, 1, 2, 3, 4, 5, 6, right? So 8 coordinates here representing the the vertex of your cube, right? So all those coordinate points I can able to represent in x1. For example, this is x1, y1, z1. This is x2, y2, z2, and this is x3, y3, and z3, and this is x4, y4, z4, and this is x5, like no. So I can able to represent each of this vertex point with a 3D coordinate, the same one we are going to do now. Similarly, for example, if I have this RGB system, and when some color is being formed, I can able to denote that color as x1, y1, z1 in that coordinate here. So this is where this is what we are going to do now, right? So now in the same case, we have an I think now you will be able to understand what is that we are trying to do. We are going to represent a new color that has been formed by combination of 3 primaries in some space, right? So for that we have 2 different models in linear color spaces. One is XYZ and another one is RGB space. First, we will discuss about our XYZ linear color space, by which so this is what the XYZ color space, right? In that, this is the cone, right? This cone, it represents the volume of all visible colors, right? For example, what we have discussed is within this 3-dimensional space. So we are going to mix up 3 different primaries, and we are going to generate different colors, right? So and all these colors will be represented with some coordinate values, right? Some x, y, and z values. So when we do represent all the colors, so within this space, it is believed that all the colors will be available, all visible colors, right, to our human eye will be visible with only within this cone, right, the conical surface, right? So the cone is nothing but the the volume of all visible colors in the XYZ space, and the vertex of the cone will be will be at its origin, right? The vertex of the cone will be at its origin. And now what we are going to do is we are going to take a plane, right? That plane is nothing but x plus y plus z equal to 1, right? We are going to take a plane, right, where x plus y plus z equal to 1, right? And that plane will be intersecting with our cone here, right? So the place where that the cone intersect with that plane, right, x, y, z plus equal to 1, we can able to see a 1, right, a curve shape here, and a shape we are going to see, uh, with this, right, we shall discuss now, right? Now if you have an understanding about this point, right, up to this point, we can discuss a little further, right? Right, and no, the where the plane intersects with this cone, right, the cone surface, we can able to, right, determine or represent this 3-dimensional, right, space with the help of 2D coordinates here, right? So this is also again like a projection, right? By what we are trying to do is we are trying to represent this x, y, z, the 3-dimensional plane in a 2D coordinate system, right? Wherein this small x equal to capital X divided by x plus y plus z. So here x plus y plus z equal to 1, right? All we know that, right? X plus y plus z equal to 1. See, this is the plane x plus y plus z equal to 1. This is the triangle, right? So within the triangle where it intersects with the plane where it intersects with this cone, we have a one no curve here, right? Half elliptical shape kind of, right? Half oval, right? So now this, right, no, we can able to represent in a two-dimensional space where small x equal to capital X by x plus y plus z, and small y equal to capital Y divided by x plus y plus z. So in this plane x plus y plus z equal to 1. So small x equal to capital X and small y equal to capital Y. That's what we will be getting it up, right? Right. So, for example, when I'm getting a color by mixing two different primaries, no, for example, A and B, right? So that no, A and B has some point in the space, right? Those no will be representing some coordinate points in the space, right? So when we join those two coordinates, no, those two coordinates, right? And the color which is forming on this, because of this mixing these two colors will also lie on the same line. For example, what no we are trying to convey here is, so I have RGB in three-dimensional space, right? So now I'm going to get a color by mixing this no R and G, right? For example, R and G. So there is a line, right? There is a line connecting the coordinates of red and green here. Now, when I see, for example, red and green, when we combine, no, we will be getting yellow. So what I'm trying to say is the yellow coordinate will also form on this line only. For example, if it is a dark yellow, close to orange color, right? If something color, that coordinate will be lying in the line connecting the R and G coordinate. See, for example, in R space, to make it more and more clear, right? R, G, and B here. So what we did is, no, insert this is X, Z, and Y. So in that case, it is R, G, B. So this is the plane what we are discussing about, where x plus y plus z equal to 1, right? And when we just dot all the these the x marks are nothing but the coordinates of different color, what we will be getting when we mix this R, G, and B value. So all those color coordinates will be lying within this conical space. That is what we are discussing now. And the point where this plane intersects with our cone space, right, cone surface, so we'll be able to see some shape here, right? So the projection of it we will see later. Now what we need to understand here is, so when we mix this R, G, and B, right, and for example if I'm mixing R and B, right, so like red and blue, I'll be getting different shades of pink, right? So now what I'm going to do is I'm going to mix this. So all the pink colors, right, will be available within this line segment only. right? So when I mix two primary colors and I'm getting a second color, right? Then that color which I'm mixing will be available within this line, right? So the next the color space model or the color space we use it instead of xyz is the rgb, right? Rgb is a color space. This is also a linear color space. uh, it uses no r, the wavelength of r no red light is 645.16 nanometer, right? And as well as for green no the wavelength is 526, and for blue the wavelength is 444. So that's why we always discuss that the range of wavelength is 400 to 700 nanometer. And when we use this red, green and blue primaries, these are the different wavelength for the each of these primaries, right? So uh, all the colors which are available within this RGB space can be represented within an edge, right? So that edge, I will be showing it. So this is the RGB color space, right? R, G and B, right? So this is the green, red and the blue. So when we mix this blue and green, we'll be getting a cyan, right? So when we mix this red and green, we'll be getting yellow, right? So all the colors which we can able to generate are can be represented within a cube, right? The conical surface, what we are getting here, right? This is a cross section of this cube, right? This is a cross section of the cube, uh, where within this cube, within this RGB cube, right? So the generator, no, or the long distance, it's represent the value here or the brightness of the pixel, right? So the angle around the cone, right? No, the for example, considering this as x and this as 2, no, this is nothing but the saturation. Right? Sorry, hue. Hue is the angle, right? No, around the cone, and the distance out gives the saturation. So distance out is nothing but how much distance it is from the origin, right? So that is our saturation, right? So when we represent the all the available colors in a RGB space, we can able to fill all the different colors available within a cube of unit length. And when we see the cross section of that cube, we'll be able to get an one cylindrical shape, right? Or a conical shape, right? So in that one, the distance is nothing but the value, right? uh, and no the angle around the cone is nothing but the hue, right? So the distance along the generator is value, angle is hue, and the distance out of generator, no. So this is where our saturation point comes in, right? So now again I repeat, nothing but RGB different color values are represented within a three-dimensional cubical space. That's it. So the distance between that two coordinate in this space will give us or infer us the dissimilarity between two colors, right? For example, if we see here the distance in coordinate space for with respect to red and green, so we can able to find that how much difference is between the red and green color, right? So, and using when we use or when we use this XYZ space, and we project all the colors available in this XYZ no, using a projective transformation, right? No, then we will be able to get an space called U dash V dash space, right? So we have XYZ space, we know that, and all what we will use is functions where the all the coordinates are positive, like that we will be using in it. And how do we represent no, with that plane where it cuts the cone, all that we discussed in XYZ no, when we use no, this XYZ space after a projective transformation, then the resulting color space we call it as U dash V dash space, right? So the distance between no, the coordinate no, in U dash V dash space, as discussed, will be indicating the difference between two colors, right? So also in the same line, we now have a CAE lab LAB, right? A color model, right? So already we discussed about all this, but anyway, to understand or represent a color, we need to reiterate on this one. So the color of a pixel will be affected by following points, right? Earlier we have studied about 3 points. Now it is clearly elaborated. So the camera's response to the illumination, right? So which means that how much of light ray is being absorbed by the lens, the choice of camera's receptor, because so depending upon that only we can able to convert those light information into a some neural signal, right? So and the third one is the amount of light that arrives at the surface. So if the surface, what if the illumination source what we are using is not up to the mark, then how do we able to no receive more light, right? So the amount of light that arrives at the surface, that's the third point. The color of the light arriving at the surface, right? So and the dependence of the albedo on wavelength, right? Because the reflective
Yeah.
power is being decided by the wavelength, right? So assume that we are going to describe a diffuse plus specular surface, right? So and wherein the x is a point and lambda is the wavelength, and E of x comma lambda is the spectral energy density, right? So of the object leaving the surface, then rho is the albedo of a surface, right? And SD of SD of x comma lambda is the spectral energy density of and S I of x comma lambda is the spectral energy density of interreflected light, right? So with this model, right, the intensity at a pixel, right, or the color, can be represented as E of x comma lambda equal to the summation of diffuse term plus specular term, because we believed that, or we assumed that the surface is diffusive and specular in nature, right? So when we say diffuse, we will be including two terms here. One is direct and another one is a interreflected term. Interreflected meaning it's not been reflected by the surface, again the color rays will be interreflecting among themselves, and it will go in another direction, right? So plus this specular term, right? So now we can able to expand this as a rho, no, that is albedo of no, for a given x comma lambda multiplied by geometric term multiplied by SD, right? SD is nothing but, right, spectral energy density of the light source. So these are no next we'll be expanding all this no diffuse, direct, plus interreflected and specular term one by one, and then we'll be looking into it, right? Right. So now, for last what we have discussed this, right? So there are different factors which affects the color of a pixel, or the brightness of a pixel in an image, right? And when we want to represent including all those terms, right? So we are going to derive a functionality. Earlier we have derived a similar kind of formula for our Lambertian and specular Lambertian plus specular model, right? So in the same line, right? So we are considering the camera is a no linear, right? And the pixel value at x is a sum of some multiple terms, right? So no wherein the different terms includes the diffuse term plus a specular term, and when we break this diffusive term, we had a direct term plus no interreflected term, right? So nothing but the light ray which is falling directly, and because of which what is the effect, and no when due to interreflection some light will fall again, so what is the response to it, plus the specular term, right? So bundling all this together, right, summing it up all together, we'll be getting it up. Right. So the three term here are diffuse, interrelated, interreflected, and specular, right? So the diffuse, the direct term here, no, can be again consider plus this interreflected term can be mathematically represented as rho of x comma lambda. The rho is nothing but our albedo multiplied by a geometric term, because also we discussed that the reflective power will not only depend upon the right the property of the surface, but also the geometric nature, right? So that's why we have the geometric term. So what we are trying to do is, what are all the different factors that will be contributing towards the color of pixel, right? So we are including it, we are trying to include it, we are trying to model it up, right? So that is what the exact word we need to call. So we are going to try to model the color, right? So the interreflected term, right, instead of it SD of x comma y plus SI of x comma y, right? So what is this SD and SIR? SD is nothing but the spectral energy density of the light, and the SI is nothing but the spectral energy density of the reflected interreflected light ray, right? So spectral energy density of interreflected light ray, right? So again, now the geometry terms, will represent how the intensity or the pixel value is affected by the normal, the surface normal, right? So also we discussed that when the irregularity, there is an irregularity in the surface, the normal will be varying, right? So that's why we calculate, or we estimate with respect to the surface normal. So always the camera is linear, right? So for example, camera is linear means that whatever the no the information available on the incoming light ray, the same will be captured, right? So that's a camera is linear, right? So the pixel values at a particular point x is considered to be sum of two primaries, right? Uh, so with this, we'll stop today. Further, we will discuss on the same, right? So what we are trying to do is we are trying to represent the color, of a pixel with the different terms, right? So this again, no, we'll have a in detail discussion tomorrow, right? So I'll stop now up to this. So tomorrow we shall continue from this point, right? So if you have any questions, no, you can ask now, or you can just drop me a mail, right?